Adnan better be bringing ice cream to class now. That better be the reason he's late. Okay. You had your chicken sandwich today?
No.
No dessert?
Yes, I have.
No, I don't want any. I'm quite full actually.
Wow.
The only thing I want is a cold drink. I'll have one after class.
You want me to tell that now?
No, it's alright. Don't want to give him an excuse to be later. Right, DIFC, physics, atoms, and now we are on to lecture 4 of 9.
What would you drink?
I don't usually drink Coca-Cola, but when it's a day like today, cold Coca-Cola always tastes extra nice. I usually drink tea, coffee, and juice, and milk. Milk is good. Kind of, don't know. I don't know if it's because as you get older, you kind of don't like drinking soda so much. Do you know what I mean? So like, when I would have drank more Coke and orange in school than I do now. I don't know. There you are. Yes, you're just about.
Me?
I don't know why you put it so tight. Well, it says 15 here now.
I'll start again.
Dude, that was 3 seconds ago.
Yeah, 3 seconds.
No, I'm serious.
I don't know about this. Okay. But why risk it and cut it so tight though?
I don't.
What do you mean you don't? Look at the time, it's 1:15. Why risk it?
Like I use, let's say like 10 minutes before, then I'm looking for my phone, for my wallet.
Oh, life is difficult. Yeah. Right, sorry, name the lesson. We'll let it slide this time, Adnan, because I use the clock in the classroom. So when I looked at the clock, it was okay. But don't risk it, you know. Like
I'll move it back for like 2 or 3 minutes.
In every
you'd have to do it in every room, and we're not usually in this room anyways on a Friday, right?
Yeah, A4.
Do it for B3.
B302,
B301, A401,
B401, we good.
It's only 4 classes. Not that.
This one is already ready. So.
Yeah, but then you run the risk if I know the clock is wrong, then I'll start using my computer, and you won't be able to change that.
No, I won't.
Alright, graphs of log A and log N. That's the title now. You got that? Yes? Oh, come on. Got it? Yes? Okay, so. Below is some data for a radioactive sample. The N, of course, you can see is decreasing. So I'm going to plot this, and you can just roughly draw it in your notebook. I'll plot it accurately, but at the very least, you can write the table down. So we have time and number of atoms, but I'm using moles because it's a big number, of course, the number of atoms. And I'm going to plot this. So can you copy this table, please, into your notebook? Yeah, it's the same numbers, actually. Now, in the exam, for goodness sake, students do such an ugly, horrible job of graph questions, and I always get complaints from Manchester when they see the graphs. So, absolutely use graph paper. But I don't know if we need a lesson on using graph paper, because when I see some of the graphs, I'm like, my goodness, that is ugly.
How would you do it? Like on paper?
Yeah, well, maybe we need to have a lesson where we use graph paper. Maybe it'd be worthwhile.
Yes.
Yeah,
It would.
it would be. Okay, maybe we will. Okay, so when we're doing our revision and when we are doing exam questions with graphs, I'll bring in a graph paper from Sylvia's office that you get in the exam, and we'll practice using graph paper. But ugly.
You see our graphs in the laboratories and mine.
Yeah, but I wasn't really counting that as being supposed to be like a good graph, because it's rough. It's a lab graph, you know. I mean, it's supposed to be good, but it's for the exam. They really want preciseness. So we shall practice. We'll have a lesson on doing graph questions, maybe graph paper. Anyway, let's plot this. So you have the table there. Yeah, so the first one is time, and what's the unit for time? Seconds. And the next one is n measured in moles. So the time goes from 0 to 10. Thank you. And we start off with 100, isn't it?
Yes. 70.02.
Hang on, I think I know what's happening here. Uh, 70.1 decimal place? I'll do 2 decimal places. I'll just do 2, doesn't matter. Yeah, so this is roughly going to be it anyways. Okay, so let's plot this. Now, I think you already know what type of graph you're going to get, right? What type of graph will we get? What's it called? What's the adjective? Yeah? Go on, yes. Exponential, correct. Yes. Exponentially decreasing. Radiation graphs are always decreasing, because radiation is something that always decreases as time goes by. I will just plot. I'll just plot the points. I won't draw it. Well, no, maybe I will. Right, so on the x-axis is time in seconds, and then n in moles.
Does the area increase?
The area? I don't think so.
Like the volume?
What do you mean? Does the radioactive material?
Or was it coming from the inside of the stone?
Yeah, I don't even think the volume would necessarily change. If it does anything, it should decrease, I think. Yeah, it's coming from inside. Yes. Okay, I won't bother with the title. Let me just shrink this down a bit. Right, there we go. Shrink this a bit more. Oh, come on. Come on, dudes. Right, I can move this to... There we go, that's a bit more reasonable. Right, there we go, now we're looking good. So you get a very nice, clear exponential decrease. Starting with 100 moles, and it's quickly decaying. After how long, or what is the half-life here? After how long until we have half the initial amount of radioactive material?
2 seconds.
2 seconds, correct. Half-life of 2 seconds. So it's something decaying rapidly. So you know, for your own sort of general physics knowledge, there are two main types of radioactive materials, really. There's naturally occurring radioactive materials like uranium, which you can mine for in uranium mines. But then there are artificial radioactive materials. Artificial in the sense that they don't exist in nature, they have to be made in lab conditions. And the difference between the two is quite clear. Lab artificial radioactive materials have an extremely short half-life. If this material existed in nature, it would have decayed away before you even get a chance to see it. So naturally occurring radioactive materials have a large half-life, like uranium or carbon-14. Do you remember the half-life of carbon-14?
So could it be like they already existed, just weren't?
Yes, there could have been radioactive materials that existed, but so much time has passed since their existence that they're no longer radioactive. You know, so things, and of course, some radioactive materials come in from space through a cosmic process, and so they always are being created. Carbon-14 is an example of this. Carbon-14 is created from radiation, gamma radiation from space. So it's constantly being replenished on Earth as it decays away. So there's always a supply of carbon-14, which is in you right now. You've heard of carbon-14 before? It's used for dating how old things are. Carbon-14 comes in and is absorbed by the plants because it comes in from the atmosphere. So it comes in from the atmosphere, it's in the air, the plants take the air in, and what do plants do when they take the air in? They release oxygen, and then the plants die and they get eaten by animals, but because the carbon-14 is in the air and now is in the plants, it's now in the animals, other animals eat these animals, and carbon-14, radioactive material doesn't break down when you eat it. It just, if you eat something that had it in it, now you have it in you. So then, the cows eat the grass, and then the people eat the grass, and then the people have carbon-14. People eat the cows, so everything that's alive has carbon-14 in it, because everything ate something that ultimately ate a plant, which got it from the air. When you die, you are no longer taking in carbon-14, obviously, because you're no longer eaten. Everybody, everything.
I ate something.
Yes.
And then I had a kid.
Yes. Yeah. Well, not because you ate it, but because the kid would have had to eat something that would have ate something that would have ultimately ate a plant. You know, like either you eat plants because you're a vegetarian and get it directly, or you eat animals. Yeah, and even if the animals don't eat plants, they would have eaten other animals that ultimately would have ate a plant. So there is no situation of any life on Earth that doesn't have carbon-14 in it. So when you die, you obviously stop eating. And that means the carbon-14 in your body is not being replenished, and then it starts to decay. By measuring how much has remained, you can date how old things are. When you think about it, a lot of things were made from something that was once alive. So old books can be dated because the books are made from trees, and the trees have carbon-14 in them. You know, Yes, you know, sometimes, for example, they might find an old campsite, and when they look under the ground, and they look and say, oh, there was a fire here, and they might find fish bones in the fire, and they can look at the carbon-14 in the fish bones, and then say how long ago this campsite was. 5,000-10,000 years ago, you know. So you can use the carbon-14 to date things by measuring how much has decayed.
So why don't the other stuff get it by touch or being close to only
the carbon-14? I think it's because there's just really not much of it in the air. Like, it's a really small amount. So it's not going to come in. It's not going to come into you by passing through your skin. If there's not enough of it, you know, it has to get into you by eating it. You know, it's in the atmosphere, but it's a low amount. Yeah. We'll actually talk about in a later lesson applications and radiation in day-to-day life, but you might be surprised to know that no matter where you are, there's some radioactive material around you. In this room right now, we'll look at this later, but do you see the smoke alarm up there? That is radioactive. There's radioactive material in the smoke alarm. It's how the smoke alarm actually works, which we'll look at later. So you can't escape radiation. It's around you all the time. Next now. So, as you can see, this graph is exponentially decreasing, which is not a surprise. It's difficult to get information from a curved graph. We can see what the n0 is from the graph, but what is the lambda? So if you look at this graph, it's quite clear what the n0 is. What is the n0? The initial value of n. 100, that's quite clear. What's not quite so clear is the lambda. So it's something we've done in semester 1. It's a proof which I said was in semester 1. I want you to practice using your logs to rewrite this formula in a linear form. Now, we did this in semester 1 when we were looking at the capacitors, which I know, of course, was a while ago, but let's see if you can recreate it. You are using logs to simplify this into a linear formula, and then I want you to tell me what the slope and the intercept now represent after you apply a log. Do you know what I'm talking about? Kind of. See what you can prove here by putting a log on both sides. Put a log on both sides and simplify. See what you come up with. What you come up with, Ms. Sharif?
So before minus 1.
Good. And the intercept?
Linear 0.
Very good, very good. And what's on the y-axis when you plot it?
Linear.
Excellent. And on the x-axis?
T.
Perfect. So if you put a log on both sides, you get log n equals log n0 e minus lambda t. Log n equals log n0 plus log e minus lambda t. Log n equals log n0 minus lambda t, because they cancel. So you get, if I just change colours here a bit to help focus, log n equals minus lambda t plus log n0. If you compare that to y equals mx plus c, if you were to plot a graph that has log n on the y-axis and t on the x-axis, the graph you get will be linear, because we can see a comparison with the linear equation, and the interpretation of the slope will be that the slope is actually minus lambda. This should remind you a lot of what you did with the capacitor lesson, where the slope was, what did we say, minus 1 over the time constant, I think it was. Anyway, this proof, again, like with the other proof, is the proof on the exam. It's essentially the same proof. The only difference is instead of n, it's I or Q, and instead of lambda, in the other one it was time constant, so it's the same thing essentially. Did I write that down on the next slide? Yeah, so what I'll do now, and you can write that down in a moment, is I'm just going to, oh, come on. Log it, yeah, and see what graph we get. Oh, dudes. I just need to move this a little bit out of the way for a moment. Right, so if I just log this. And don't worry, I have the results for you in a moment. Copy this and paste this here, and then delete this and move this back over here. So now, can I change the... Yes, I can. So this is now log n in, and the unit will be log moles. Right, so what I've done is I've applied a log onto the values of n, and you see I get a nice straight line now. And I have the numbers here for you to add to your table. But before you extend your table, I think it'd be good practice for revision and memorizing to write the proof down if you didn't get it. Yeah, you wrote this down already?
No.
Oh, okay. You did it the same way?
Thank you.
Huh? Yeah, we see this is Mushari's reward for all his times he came to class at 9 o'clock and he was the only one there.
No, that had nothing to do with it. That was last semester. We were all there.
Yeah, that's true.
We were over there.
Not only were you all there, but there's actually more there.
Yeah.
Alright, you got this proof? Yeah. So, this is log n, and I think it'd be... No, actually, that reminds me, in the exam, sometimes that's actually a part of the question. Mushari, just one sec, listen. Yeah. In the exam, sometimes they would say, here is the data for t and n, and then they would say something like, extend the table, or produce a suitable row, or in other words, they'd use some verb to say, make the table bigger, and they wouldn't necessarily tell you what to add to the table, but you'd have to know that for radioactive problems and capacitor problems, it is going to be the case that you'll need the log of y instead of y. So I've seen a couple of questions where they give you a table and leave a blank row, and they would expect students to put the log in. Now that's actually extremely easy to do because you're just hitting in log on the calculator. But they might not say to use log. They might use a different verb like extend. You know extend?
Yeah.
Increase, you know. So I think it'd be good if you can add this to your table. And can we think of some verbs that might be suitable here? Extend is one verb. Any other verbs? Expand, I guess, is okay, yeah. Continue, yeah. And what about some adjectives? Yeah, but an adjective that describes this row. So we can't say log because they won't use log. That's part of the question. So what adjective could we use here? Well, we have adjectives like suitable. You know, suitable, appropriate, convenient. Yes, perhaps convenient. You know what I mean? Though, avoid using a word that gives you a clue that you're to use log. Okay, so if you can add this to your table, please. Add what? Add this to your table. Dude, you're breaking my heart. Alright. You've added this row, Ms. Sharif? Yeah? Yes? Yes, yes. Okay, okay. Back to my graph. So, oh rats. Did you draw down the exponential graph?
Yeah.
Okay. Can you draw this graph? Now again, you don't have to be perfect, but what I want to see is at least on your graph that you start here at about 4.6 and it goes down to about 1.1, as you can see, after 10 seconds.
Log mode.
I think so, yeah, because you're just logging the mode. Yeah. You have that drawn, Adnan? Mushari, you drew this? Yeah. And Iyad?
Yes.
Yeah.
Good.
So, we've seen what happens. We've seen what happens when you put log on both sides. We end up with this formula, and so we have y equals log n, x equals t, m is minus lambda, and c is log n 0. So, in fact, if you did the same thing with a instead of n, no surprise here that you get a remarkably similar result. Except why? What is the problem? Big problem. How did you do that? This is a Mushari problem. That is it. Do you cause this much trouble at home? Only in school? Yeah.
It's a problem.
No, it's not. Log activity. So you got y equals log a, x equals t, but again, the slope is minus lambda, because in the formula it's still minus lambda here, and of course c equals log a 0. So my point is, whether you log n or log activity, in both cases the slope is minus lambda, the decay constant. And I think that is worth noting, these two formulas. Now, you probably have this one here because we just proved it, but if you can make a similar note for the activity, you get basically the same results, only slightly different.
And for the math.
And for the mass too, yes. Although, in the exam, they only ever ask for N and A. Yeah? Yeah. We have an example. Okay. Right. So, this one here we'll do this one together. See how in part A I say graph this in an appropriate manner. I don't actually say what graph to make. A common mistake in the exam will be students just rush in and plot T and A, but of course that's wrong. What's the first thing you need to do? Log A, yeah. Okay, so we'll do this one together. You'll need your calculator. Now,
So I should always look
unless the question said not to or to plot A, if the question used the adjective like appropriate or suitable, then yes, you would need to use log, because these are the right ones to be used. And the question will have to be very explicit for you not to do this, because it is appropriate to log it to make a straight line. So the very first thing you need to do after you write the table down is to log the A. You got your calculator? You got your calculator?
Yeah.
Okay, we all got calculators, so we can all do this one then.
I can do mine only, or you can use this only that in.
You don't have a calculator? Oh, I thought we had all three. Okay.
We have to.
3 Casios. What the heck is that? Is that even a Casio or a Sharp?
Sharp.
I hate Sharps.
Why?
Don't like them. Casio is so nice and friendly and easy to use. It is friendly. Okay, have you logged the first row? The second row? You've logged it? Yeah, so we'll graph it now. Wait, so let me just give you some pointers on making the graph. Whoops. Okay, so can I go to just the A4 pad here for a sec? Now, try to use as much of the page as you can. Iyad, what's the smallest time? 0.
I didn't do the, I didn't write the table.
Oh, that's fine, that's fine. And what's the biggest time? 10. So, tip number 1, don't go to the edge of the page. So if there's 10 seconds, you'd want to leave enough space to get to 11 or 12. So let's imagine that this is the end of my paper. I should think of this as like 12, so I'm trying to get to 10 here. So if I split it up into 10 pieces, that's 5 and 5. So I need this to be in 5 pieces. So if you measured this with your ruler, you could get it exactly right. But in graph paper, you have the squares, so you can count the squares up. You know. So anyways, I'll just do it roughly. 1, 2, 3, 4, 5. So this is 5 seconds. 1, 2, 6, 7, 8, 9. So this one will be 10 here, and that's 11, 12, 13. So this is 10 seconds here, and this is time in seconds. Now, what's the smallest log A? 0.57. And the biggest? Okay. So if we go up in 0.5s to 2.5, so we have 5 pieces. So we'll have here to try and be 5. So 1, 2, 3, 4, 5. And this axis is log activity in log mole equals. So the unit is moles destruction of atoms per second. So for example, 1 would be 1 mole destroyed per second of atoms. Alright, so we're going up in 0.5s. Okay, so I'll just put in some rough grid lines just to help me focus. You, of course, don't have to, but we want to at least get it vertical. Right, so Iyad, what was the first value you got?
2.3.
And Musharif, what did you get? 2.3, good. So 2.3 will be here.
Oh. Yeah.
Yeah, because we're starting at 0.
Yeah.
Right, the next one, what you get?
8.41.
Did you press LOG, dude?
No.
LN what?
8.41.
LN 10. What did you type?
The next one
He
is
just did the
Alright. What's the next one then?
2.1.
2.1? Hang on, let me just put over these lines. Right, next one?
1.96.
Yeah?
1.96.
Yeah.
1.78.
Mm-hmm.
1.6.
Mm-hmm.
1.44.
Mm-hmm.
1.26.
Mm-hmm.
1.09.
1.09. 1.09.
0.92.
Mm.
0.74. And 0.57.
Roughly. So this is what your graph looks like. Roughly. Not perfect, of course, roughly. So we have just done first part. Second part, estimate the lambda. So what is the lambda here? It's equal to minus the slope, which is minus the rise over the run, or what we call, the y over the x. So if in the exam, what they want to see on your graph is an attempt to calculate it by drawing a triangle. So the bigger the triangle, the better. So if I go from here to here and make a big fat triangle here, and measure this length. So this is from 2.5, and so this is 3 units, is it about?
No, 2.3.
2.3 minus.
Yeah, 2.3 minus 0.6. So what's that, about 1.7, is it?
Do we have to start from the first dot when we go?
No, we don't even have to do that. You could do the triangle like here even.
No, I mean the line. Because we should get that points of line.
You don't even, no, you could even do it for points not on the line. Like you could even do it for this triangle.
Yeah. I mean the line, the red line. When we first draw.
Yeah.
Do we need to start from the point on the left, or can we just move a bit above?
Oh, we can. Yeah, we're trying to fit as many points as we can.
Yeah.
Okay. What length is this, Iyad? 1.7. Yeah. Okay. And obviously the bottom is 10.
So 0.20.
Yeah. Oh, and because it's going down, it's a minus, but I already have a minus here, so it's actually minus 0.17, which is 0.17. But anyways, you know the decay constant should be positive anyways, so you can fix the sign knowing that it should be positive. This is sloping down, meaning it has a negative slope. So the formula is minus the slope.
Yeah. So shouldn't it be minus 0.17?
Minus 0.17. This slope is, the m here is minus 0.17. And the formula is minus m. It is, because it's going down. Remember, downward lines have negative slopes. Yeah. Now, we have a small problem with the units because the decay constant is in per seconds. But we're not using atoms and seconds, we're using moles and seconds. So we better double check the units. Question, Sharif? Yeah, what's the question?
Why the slope is minus 0.17?
He just asked me that. So he is going to explain it to you, because I'm not going to repeat myself.
So it's going down, so it's minus.
That's what he asked me, that's what I answered, and he was happy. Are you happy too? Great. Okay, so let's double check the units here. So the units for the lambda will be the same. The units for the lambda will be the same as the units for the slope. We don't care about the minus because that doesn't change the units. So what's the units for the slope? Well, that's the units for the y over the units for the x, which is really the units for y2 minus y1 over the units for x2 minus x1. So that would be here the units for log activity 2 minus log activity 1 over the units for time 2 minus time 1. Well, the units for time is seconds, the units for time is seconds, and the unit for time minus time is also seconds. 10 seconds minus 2 seconds is 8 seconds, so quite clearly the bottom is seconds. So what's the top? Well, log A2 minus log A1 is equal to log A2 over A1. And whatever the units are for activity is not important because they will cancel. So we are unit free on the top. Because we are dividing here. So it didn't matter that we were using moles or kilo or micro or mega number of atoms. It was irrelevant. The only thing that mattered was what we used for the time. And this is what we wanted the K constant to be in, is per second. So the units are fine for this. It is still per second. In other words, the units here will match the units here. Okay, that is good. So that answers part A and B. Part C, what is the half-life? Well, now that we know the decay constant, we know the half-life. The formula was log 2 over lambda, wasn't it, for the half-life?
Yeah.
So can you hit that in, please? Log 2 over 0.17? 0.69 over 0.17. So what's that, 3.5? 4?
The table.
Yeah.
Wait.
The half-life is 4. This should be roughly 4. What did we get?
4.07.
Yeah, close enough. 4 seconds. Right, next one. What is the n0? Well, actually, I don't need the graph. It's quite obvious here. The activity is 10, so we just need to change the activity into n. So what formula do we use here? A equals minus lambda. Remember this one? So then the n0 will be A0 with a minus over lambda. So that would be 10 moles. How many atoms in a mole? Avogadro. So I'll just write N. What power do you use for Avogadro in chemistry? I write Na for Avogadro's number. What do you write? Or not anything? Okay. Just, okay. And then over 0.17. So if you can hit that in, please. No, you know what? I'm going to leave it in moles. There's no need to change it. So just what's 10 divided by 0.17, please?
58.8.
So 58.8 moles. That's how much I have. And then lastly, what is the n at time 11? So I have to shrink it here a bit. Well, we know this one. This is n equals n0 e minus lambda t. That's 58.8, but these are in moles. E minus 0.17 times 11 moles. So, Ian, if you don't mind just hitting that in.
Nine point
9.06 moles. What's wrong, Adnan? Is it okay?
Yeah.
Adnan? Okay. Right. Do you need to write this down? Or probably do. Sorry, it's a little bit muddled up now. The first part was the graph, which is here, obviously. Part B was the lambda, which is here. Part C was the half-life, which was here. Part D was the n0, which was here. And then lastly was part E, which is the n after 11 seconds. Okay, you can write that down. Yes. You will come back, won't you?
Surprise you.
Okay. You can surprise me. So he's going to leave there. I'm going to surprise him by not coming back. I said, my joke is, your surprise for me is that you're not coming back. But that's a bad surprise.
Why?
Still a surprise.
Oh, you think that's a good surprise for me if you're not in class? No, that's a sad surprise.
I think you hit my face. You told me everywhere.
I'm not sick of your face. Is that what you said?
Yeah.
No. I'm not. I'm sick of his face.
No.
Really?
No.
You don't need to see his face.
Exactly.
You don't need to.
Exactly.
Tell me.
Exactly.
Okay, okay, that.
Yeah, don't go overboard now. Alright, did you write this one down? You're writing it, okay. Got that, Iyad?
Yes. When we calculated the time in C, and the answer was 4.07. It wasn't exactly 4, even though we can just say from the table that it's 4.
Yeah. Yeah, I don't really think that's actually a realistic exam question because, like you said, you can see it from the table. So they'd probably give it to you in such a way that you can't see it from the table. Is that what you're asking?
Yeah.
Yeah.
Also, like, if I do have it in the table, for example, and my answer wasn't precise, it was like just a bit off.
There's an acceptable error amount. 4.07 to 4, I would give it.
Yeah.
Yeah. Okay, you got that, Anna? Okay, so now, here is one for you to try. Everything's the same. It'll give you a good chance to practice, and then we'll have a look at an exam question for this. You got a ruler with you? Do you have a ruler at all? Okay. It would be worth buying one before the exam, if you'll need one.
Yeah.
Okay. Well, can you do your best without a ruler, please? This is the
What?
what foreign lesson?
Every subject?
The first lesson. Graphs.
Oh, the graph.
Yeah.
Mm.
But they're good for the exam, you know, they're easy marks.
No, they're not. They weren't.
Okay, fair enough. They should be easy marks, really. Alright, well do your best here now. So what's the first thing you need to do before you do anything?
Log A.
Log it, yeah. And please note, the unit is mega equals. I would leave the mega in there because remember we learned that this does not affect the units on the lambda.
So it's still per second.
Yeah. However, you must consider the mega when you're calculating the ends. Yeah, and that's fine. So this slightly complicates your graph because you'll have to go under the x-axis at the end.
It came into it.
So,
Just thinking.
aye.
You show how this solution.
We're making this graph. Okay, started.
What is it? So C is 4. Yeah?
It is. He means part C, the half-life is 4.
If you finish early, we can.
I want to do an exam question after this. Then I'll be happy. Sharif, you weren't here for the last 10 minutes, so like...
It's only 10 minutes. This is very easy.
Not yet. Hang in there a little longer.
You can make it. You can make it.
You're strong. Be strong. Look, Sharif, we're just going to do this question, then an exam question.
One example.
One exam question. I don't ask too much, I think. You don't even have any homework.
But we have still time.
Okay. Well, then it's a good thing I'm not giving you any homework.
Thank you.
Oh, you're welcome.
Is it the only question we're doing?
No, calm down. It's not. No, it's nice. No, it's that. I said this and one exam question.
Oh yeah.
This is the homework. This is the only
Yeah, it's okay,
question.
but
I'll do.
it's not that I don't want to do anything. It takes long. Grasp.
Be strong.
We do it perfectly, the three of us.
Do what perfectly? Oh my goodness!
Yeah,
what- You don't even have a ruler, all right?
I can leave early and use my fingers also.
Y1 is ln 5.
The first one is log 5, yeah.
I mean Y1 is ln Y1 is it ln 5?
Yeah. Why? What's confusing you? The first point, the first y, is log 5. The last one is log 0.885.
the lambda is the same as the previous.
Not regular.
No, he says the lambda, the decay constant.
Ah.
He hasn't calculated yet.
What do you mean by lambda?
I don't.
Because the one is not the same.
Yes, but I think Mr. Reef might be right when you calculate it.
Yeah,
See what
I
happens. Yeah, yeah.
Did you throw it down? Oh, you didn't.
But why do I use the N0 minus?
Because you forgot to say the activity is minus. No? What did you say A0 was? 5?
Less 5.
Yes.
N5 over my decay constant.
Huh? Are you which part are you talking about? D, is it? No, shouldn't be log 5. Because the formula is A equals lambda n, not log A equals lambda n.
So it's only 5.
Ah, no it's not.
5.
It's not 5. Look at the unit for A.
5, 10, 6.
Come on, add get a graph in there. I know you don't have a ruler, but you can still get it in rough.
I need one more line for me.
You need one more what?
Yeah.
Too short?
Mm.
What's the highest point on it? On the Y, what's your biggest Y value?
I want to make it 1.7, because the biggest is 1.6.
What did you get? What, can you read out the table? What's log 4.21? The second value.
1.44.
And what's log 5?
Number 5, 3, 5.
Log 5. The first one.
1.6.
And what's the biggest value on your graph?
1.6.
So you have enough space? Huh?
0.16.
What's that?
The smallest is minus 0.16.
Yeah. And your graph goes up to 1.7, does it?
Yeah, but there's not enough space here to make it like 1.5, for example. 1.6.
Oh man. What are you doing, man? What are you doing? Are you going up it?
Mega.
No, what unit are you increasing it? By how much are you increasing each time?
3.
Yeah. So 0.1, if you add point...
No, I went down myself. Because I didn't put that zero.
Whatever. No, why you should be drawing a graph, those facts. Go up.
Yeah, anyway, but I thought that this would be better.
1, 2, 3, 4, 5, 6, 7. And the biggest value, it goes from minus 0.2 up to 1.7.
0.1.
Okay, and it goes up to 1.6.
1.6.
And you have 1, 2, 3, 4, 5, 6, 7.
I want to make this 1.7, but there are some like areas. So the doesn't start from the top.
Yeah, no, straight. There's no time about it. This is 0.
Okay.
This is penny. That's 0, right? That's 0.3, 0.6. You go from 0.3 is 0.6, 0.3, 0, 0.3, 0.6, 0.9, 1.2, 1.5, 1.8, 2.1. You can go up to 2.1 if you go up from 0.3. And then this is minus 0.3. Look, no space here. And you can even use the lines. So these are going up into 0.3s, 0.3s. Can I, oh, very nice. You got your graph there? Yeah, that's good, good. You're getting the decay constant. Excellent, excellent. Mishri, you got your graph? Very nice, very nice. Keep up with the work. Keep going, man, keep going.
The line depend on the
Oh, okay, well, when you have graph paper, it'll be a bit better, I'm sure. Did you get the decay constant, the slope now of this? Yes? Did you finish this?
Yes.
Oh, okay. Mr. Reeve, did you finish it? What did you get for your part D, Mr. Reeve?
29.4, which is not 10 to 6.
You got the same? Yeah. Okay, very good. So this one's no trouble. So let's have a look at that one exam question. So last time, do you remember we were having a look at the iodine question with the patients? Do you remember that, the thyroid?
Yeah.
Yeah. No, I think that was another one, the radon 222. I think that's what you're thinking of. Right, let's see what the other half of that question was. What's wrong, Moose Sharif?
No, nothing.
Right. This question was extra nice because they told you to calculate the log. See that?
Yeah.
How many marks for doing the blooming obvious here of calculating the log? 2 marks. Can you imagine how shocked I was that not everybody got this right? Can you picture me correcting the exams and then looking at one student's paper saying, but it said in the question log activity, and it gave me the activity, so all you had to press on the calculator was log, and yet that student didn't get it right.
I know why.
Go on, tell me.
Last time when I was doing the work, one time I do log activity, and the second log the time, and third log the activity, next log the time. You know?
Maybe they did this.
Yeah.
Anyways, if you did this, you would shock me. Yeah. Anyways, do you see how part 2 is a proof?
Yes.
Part 3 is the plot, part 4 is the K constant, and part 5 is calculate the half-life. How many marks for those 5 parts? Add them up. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. How many marks on the exam?
14, 10 marks.
No, how many marks on the exam? 100 marks. So if you drew this graph question correctly, what percent is that of your grade? 14%.
So the proof part is always in the graph?
No. This year it was. This year it was.
Which
Yeah.
year?
This is 2000
Oh,
15, yeah.
I wish if they get
Because you know it's
again.
There is good news for you. Good news. Every exam always has a graph question. I've never seen an exam without a graph question. What graph they ask you changes. This year, the graph question was this.
What would this get?
Let's see, do you have... Well, if you did it on graph paper, that's all fine. Although that 1 point sticking out by itself is a bit odd. We'll do this one, and then we'll go.
Yeah.
What's wrong with you?
Like the
Wow.
log is calculator, and the blue is bigger.
Who has their laptop?
No.
You don't? You don't?
Why?
You don't?
Why?
I was going to say you could do it on your laptop if you wanted.
Say after I see.
I'll tell you what. I'll strike a deal with you. You can do this. Can be a homework then. Yeah, because I just wanted you to practice another graph one. So if you do this one at home, now this one's not on Moodle, so you'll either have to watch the video because the video is still recording, or you can take a snap of this now. And I am going to check your one first on Monday because you're the one who really wants to go now, and you might be the only one there on Monday.
Monday we don't have physics.
We have physics from now on.
No, we don't have physics.
What do we have on Monday then?
We have the last lesson,
On what?
practical.
Did you watch the video? So I said I'm only doing that after you watch the video and decide if you need it or not.
Did you check the new timetable?
No,
Do we
why?
have next week? Do we have as many hours? Okay, wait. Math.
No, hang on. Listen.
This is important, very important.
Yeah, we
It's
have.
not mere, is it?
No.
Oh, good. Next week, there are two things happening. The January students have their exams, and the January students have their labs. So, for example, Lorraine or Svata, they could be at the lab in DIT for the whole day, therefore no chemistry, for example, or whatever, I don't know. So if your timetable looks like you have less hours for next week, that's a possibility. We may have to have cancelled classes because the teachers are tied up in labs and exams. Why? How many hours do we have next week?
Yeah, that's all.
How many hours?
Yeah.
Monday,
6
4 hours.
by 12.
No.
Wait,
You were explaining to him that you have lab record.
4 hours on
Okay,
Tuesday, 2 hours